So the next speaker is Christoph Herrmann, together with Anna Wilsch. And Christoph is at the Karl von Ossietzky Universität in Oldenburg. And he will speak about transcranial current stimulation with speech envelopes and enhanced intelligibility.
Yes, thank you for the invite and for the introduction. I would like to talk about something that you may or may not know, transcranial current stimulation, and it gives a new view onto brain oscillations because it is able to modulate brain oscillations. And by modulating the brain oscillation, you actually can show that there is a causal relationship between the brain oscillation and a cognitive function, because you modulate the brain oscillation and you look whether in turn some cognitive process changes. So that's what I would like to do with you today. In the beginning, I would like to talk about the mechanism for those of you who don't know the mechanism yet. Then I will show you the physiological effects, what parameters of brain oscillations you can modulate. And then at the end, I would like to show you that we can modulate auditory perception and, for you probably most interesting, also speech intelligibility. So what does that look like at first? You have to place at least 2 electrodes on the scalp of a subject, 2 or more, as you can see on this little styrofoam head. And then you can either apply tACS, or I'll explain all these different versions of the stimulator. The one that you see on the left is battery operated and portable. And there is another one, or there are different brands of course, but there are different types that are less portable and only to be used in the lab, but then they're more versatile and have more channels, and you can be more spatially specific with the stimulation. When you think about the type of stimulation and the waveform that you can simulate, what has been around for the longest is tACS, where you apply a direct current. So you switch on the current, and then the current stays on for some 10 or 20 minutes, and then you switch it off again. This is not what I'll talk about. And then what's more interesting, because it interferes with brain oscillations, is alternating current stimulation. I will talk about that, where you switch on an alternating current of, say, 10 Hertz to interfere with the alpha for, again, some 10 or 20 minutes. But in principle, any waveform that you can generate in MATLAB can be input into the stimulator, and then it's actually being stimulated on the head. So you could take impulses, you could record the EEG of someone and play it to someone else, or, as I will show, you could use the envelope of speech to use that as an electric stimulation. And just to be complete, there's also something that's called transcranial random noise stimulation, where you take band-limited white noise and use that as the stimulation signal. One of the questions... Good morning. One of the questions that many people ask is, well, you're applying a very low current, like a milliamp, to the scalp. And the scalp is very well conducting. And then there's the skull, which does not conduct very well. So the question is, how much of the current does actually go through the skull, into the head, penetrates the tissue, and can, in principle, interact with neurons? And for that, you can do simulations with finite element models, and we did that together with a mathematician from Münster, Carsten Wolters, who has a very fine-grained model of the brain with more than 2 million voxels, and every voxel is a tensor of conductivity, so it has a direction, and many different parts of tissue. So for example, the bone has 2 subcomponents, the solid bone and the spongeous bone, because they have different conductivities. And we were able to show that that's really important and influences the predictions. And then you can place your electrodes. Here we have 2 rather big electrodes of 35 square centimeters. And then you can look where in the brain we switched off the skin here, because of course, yes, there is much more current density inside the skin. But if you choose a different range and then switch that off and only look inside the brain, you see, yes, also inside the brain you have current density that is due to this electrical stimulation, and it has some spatial specificity. So beneath and between the electrodes there is more current density than further away from the electrodes, and it's on the order of 0.1 amp per meter at the max. Remember that, because That will be important on one of the subsequent slides. And if you use more smaller electrodes, you can be much more spatially specific with your stimulation, as shown here, for example, where we have two 4x1 montages over the two hemispheres, and you can see this is almost the spatial specificity that you can reach with TMS, for example. Another interesting question is, if you have this low intensity on the skin, does that actually do anything to the firing of neurons? Because that has been called in question, for example, by Bujaki. Now, the animal experiments that actually look whether a voltage applied to the cortex changes neural firing or not is usually given in volts per meter, a voltage gradient, and where tACS intensity is given in milliamps. So we have to get there in a few steps. The first step was what I showed you on the previous slide, where we used the finite element model to see that 1 milliamp of tACS, of course, has a range of current densities inside the brain, but in the target region, it's about 0.1 amp per square meter. Then you need to know the tissue resistivity, which is given in ohmmeters, and which is also being argued about, but it's on the order of 3 ohm meters, and then this converts into 0.3 volts per meter. And Bujaki compares that to a study where he's a co-author, which showed that you need 1 volt per meter to interfere with neurons, but there are a number of other studies, for example these, that show that also much lower voltage gradients interfere with neurons. They do not make a silent neuron fire, but if the neurons are firing, because they get input from other neurons, then the spike timing and the spike rate can be modulated by tACS. And you see that the 1 milliamp is in the ballpark of intensities required for that. So we believe, yes, it does work. And yesterday already, Jonas said something about entrainment, and he already said that I might go into this concept into more detail, because we believe that if you use tACS in order to interfere with the brain oscillation, what's being at work is entrainment, and if I have time, I'll come back to that later. I would like to guide you through the left figure at first. On the horizontal axis, I always have the driving frequency, so in this case, the tACS frequency. And here I have the response frequency, so in this case, the EEG frequency. If you leave the system alone, you just see it at its eigenfrequency. So, for example, the alpha frequency if you have a human subject at rest. If you drive the subject very strongly, then you only see the driving frequency, no matter whether you flicker or use RTMS or tACS. These are both not conclusive about entrainment or not. Interesting is if you have some intermediate driving force, because then the brain switches between two different regimes. One regime is it shows its eigenfrequency. But if the stimulation frequency is in the vicinity of the eigenfrequency, then the system will follow the driving frequency. That is the synchronization regime. And now you can put this into another diagram, which Jonas showed yesterday. Here you have the driving frequency and the intensity. And what you see here is that if you have a very low intensity, then you need to be very close to the eigenfrequency in order to modulate the system. But if you have a very strong intensity, then the region where you can actually drive the brain or the oscillator becomes much wider. But interestingly, this goes down basically to 0. But then, of course, it's a very narrow range where you can do something. And Flavia Foley did a very nice study where they recorded activity in rat cortex, at first without sinusoidal electric stimulation. That's shown in black. And here you see bursts of neural activity and interburst intervals. And then he applied electric sine waves to the cortex at different frequencies. Let's start in the middle. Here, the sine wave frequency is roughly that of the interburst frequency up here, but you still see an effect because the spiking becomes more regular. The neurons spike during the troughs of the oscillation, but hardly ever during the during the peaks, but hardly ever during the troughs of the oscillation. And then he can slow down the interburst frequency or speed up the interburst frequency by changing the frequency of the sine wave that he is applying. So this is one evidence for entrainment being at work. Now we wanted to show that when we apply tACS to the human brain, we can actually interfere with brain oscillations, and we will look at the online effect, so that is what is happening during stimulation, and at the offline effect, that's what's happening after stimulation. And here we recorded EEG during the tACS session, which is possible in principle, but you have a huge artifact. You see this huge sine wave, which is on the order of volts as compared to the microvolts that you want to see. But if you can assure that your EEG amplifier is not clipping, you in principle can get rid of the artifact by subtracting it. And what we did in addition is we had a visual task where an LED would change the color, and that should in principle induce an ERP, so we can see whether after artifact reduction or removal we can actually see this ERP or not. And the artifact reduction went in 2 steps. The first thing is that you try to compute a template of the sine wave, which is of course not a sine wave but a rectified sine wave, and that works okay-ish. You see the magnitude of the artifact goes down, but in some trials there's quite a residual artifact. And therefore, in a second step, we computed a PCA and subtracted as many PCAs as were necessary, because we know a couple of things. If this is the electrode montage, this is the topography of the artifact. And since we stimulate at 10 Hertz, this is the spectrum of the artifact. So we could look whether the PCA component looked like these 2 things, and we could look whether after artifact subtraction the ERP would look like the ERP that we would expect. And then, of course, that's individually different how many PCAs we have to subtract, but as you will see from the ERPs, these are the ERPs of a group of subjects that did not get stimulated. So this is the ground truth for us, and you see the morphology and the topography of the ERPs to the standards and targets. And these are the data from the subjects that were stimulated with tACS at 10 Hertz after subtracting out the artifact and computing the ERPs. And I hope you're convinced that they're not the same, they're different subjects, but you see the difference in P3, you see the morphology, you see the topography, it's very much alike. And this is of course not what we were after. We wanted to see, well, what is happening during simulation? On the left you see what is happening for the sham group. There are no significant differences, but here you see 2 interesting things. One thing is that you elevate the amplitude of the alpha during stimulation. That's the gray spectrum. But in addition, you make it more narrow. So we think that is, again, evidence for entrainment. We think that subjects who had their individual alpha at 9 Hertz were speeded up to 10 Hertz, and subjects who had a faster alpha were slowed down to 10 Hertz. And in addition, you see already the after effect. The green spectrum was recorded during the 3 minutes after the end of simulation. So you see that the elevated alpha amplitude remains there after the end of simulation. And now we also can look at the time course during simulation. So on the left side, we see the sham group again. And since when the stimulation is, or the task is being switched on, it's a visual stimulation, you see the alpha go down, but then it's a rather boring task. The alpha increases over time. And in the simulation group, the alpha immediately goes up because of the tACS, and then it remains elevated also after the end of stimulation. And that was only, then we looked at the after effect in a different study, where we wanted to see, actually I think I'll skip that because I already showed also the after effect for the sake of time. You see already here that there is an after effect after the end of stimulation, and then it's more certain that I can actually show my slides at the end. But another question was, well, how long does this after effect remain stable? And at first we only looked at 3 minutes, then we extended the interval after the end of simulation to 30 minutes, and we expected that we would see it decay over time, which didn't happen. Then we extended it to 90 minutes, and we expected that we see it decay over time. You have a question?
How long was the stimulation?
The stimulation was 20 minutes in that case. And here you see how the amplitude of the alpha peak behaved over time after the end of stimulation. And you can see it does not decay back to 0, but instead what happens is that the alpha in the sham group raises over time. So after some time, the difference between the two is no longer significant, and that was after 78 minutes or so. So on average for a 20-minute tACS simulation at the individual alpha frequency, not 10 hertz, you get a 70-minute after effect of elevated alpha amplitude. Once we knew that, we, of course, wanted to show that this is any good for some cognitive function. And we did a couple of other studies in the visual system, which I will not show here because we're talking about the auditory system and about language. And what we did here is that we applied tACS exactly at 10 hertz, and then we had an auditory task where we had white noise, and embedded in the white noise, we had brief impulses of sine waves that were supposed to be detected. And these sine waves were presented at different signal-to-noise ratios. I mean, here you can clearly see it, and here you can clearly hear it, but some of them had such a bad signal-to-noise ratio that they were not detected by the subjects. And they were placed always relative to the tACS wave in different phases of the tACS oscillation. And what we then did is we computed the sigmoid function for the different intensities or signal-to-noise ratios and for the detection rate of these sounds. And here's a single subject, and you can see already what's nice. In relation to the red sigmoid function, which was without TDCS, you could, we called it alpha TDCS back then. Today I would call it tACS basically. You see that the different phases can both make it worse and make it better, the perception. And that was already nice to see. And if we look at all of the subjects, here you see the alpha wave again. And here we sorted the subjects because every subject had the best performance at a different phase. We sorted them, but then you see all the single subjects and the mean performance and a sine wave that we fitted there. We couldn't use an ANOVA because, of course, the average of a sine wave is 0, and therefore what we tried to do is we tried to fit a sine wave into the data, which is shown here. So you see each single subject in blue, and then you see the mean fit in red. And here I took out 2 of the subjects so that you see that the sine waves that we fitted, which are shown in black, resemble the data points which are shown in red pretty nicely. So we think, yes, we are able to modulate auditory perception if we apply a sine wave to the auditory cortex. And the reviewers are usually not so happy with nonlinear regressions of sine waves, and therefore we also had to do a t-test of the best phase versus the worst phase, and you can see that is highly significant, which made us happy, of course. And then I have to tell you a little anecdote. In Germany, the supervisor of your PhD thesis is called your doctor father. And in Germany, you have to do a second PhD thesis, which is called the habilitation. And there I actually happen to have an academic mother. Angela, who is no longer here today, is my habilitation mother. And as a good boy, of course, you're trying to impress your mother. So when I was able to do something with tACS, I went back home to the Max Planck Institute in Leipzig and gave a talk about what I showed you so far. And I was so happy, and I thought I would impress her with the things that I had done. And she said, well, Christoph, that is all very nice. You can modulate a brain oscillation, that's cool. And you can modulate auditory perception, that's okay. But why don't you try and modulate an important cognitive function? Okay, an important cognitive function. If Angela says so, she must be referring to something like speech or language, right? Okay, we tried that. It kept me busy a couple of nights. What can you actually do to impress your mother? And to improve speech by tACS. And as we all know, if you listen to language, you can see the envelope and neurons entrained to the envelope. And interestingly, if you know the envelope of the speech signal, you can see that in EEG and MEG. And more interestingly, if you start to compress the speech and present it in a faster way, then at first the frequency of the envelope just increases, and you still see that in the MEG. So here you can see that below 10 Hertz, you can see a resemblance of the speech envelope in the MEG signal. But at some frequency, which again differs from subject to subject, two things happen. The brain cannot follow the speech envelope anymore, and the intelligibility of the speech breaks down. So the idea is that the envelope and the envelope being visible in the EEG is important for speech intelligibility. And then we thought, okay, since we can not only stimulate with sine waves, we try to use the envelope. We had a bunch of sentences, as I'll show in a minute. We extracted the envelope and then tried to stimulate that electrically at the same time as we presented the auditory sentences, as I'll show you here. So at first we measured the thresholds of the subjects because they shouldn't know whether they're being stimulated. So if you apply an alternating current to the skin, and if the intensity is too high, it feels a little bit like a tickling sensation. I don't know who of you checked your toy batteries when you were kids with the tongue, the 9-volt batteries. If they were full, that was quite unpleasant. If they were empty, you would still feel that, and this is what tACS feels like if it's too intense. So we stay below that threshold, and also if you apply it over the back of the head, you can induce phosphenes. Then we determined the hearing threshold, and then we presented sentences that you will see on the next slide, and did 9 lists of this during tACS, and that works as follows. So for the 2 auditory cortices, we will have current flow from T3 to CZ and T4 to CZ, and instead of applying a sine wave, now we actually use the envelopes of the speech signal. You see the sound pressure here, and we extracted the speech envelope and applied that electrically to the scalp, such that that would then again be an electric signal in the auditory cortex, which would hopefully entrain the brain activity. The sentences were all of the very same type. A bit boring, you might say. Britta hat 8 weiße Bilder. Britta has 8 white pictures. You see the sound pressure at the top. And then, of course, if we present the auditory signal to the ear, and we want to present an electric signal to the brain, we need some latency in between, because the auditory signal needs some time to travel to the auditory cortex, and we didn't know beforehand whether this would be 100 milliseconds like the M100, or would it be 50 milliseconds like the P50, or would it be some other latency. And therefore we decided to try out a couple of latencies from 0 to 250 milliseconds, and to see whether any of them would actually interfere with the intelligibility of these sentences that were presented in noise at different signal-to-noise ratios, always in such a way that some of them were unintelligible. And the subject who sat in a cabin had to say the sentences into a microphone, and then afterwards we evaluated how many words were correctly perceived. And as sham conditions, we had one, or as control conditions, we had a sham condition where we didn't apply speech envelope tACS, and we had 2 DC conditions where we applied anodal or cathodal TDCS to the cortex. And of course, our expectation was that this does not interfere with speech intelligibility, and at least one of them would do. Okay, now you're set for the results slide. So here we see the signal-to-noise ratio of the 50% threshold of the sigmoidal function for the 3 control conditions. And here we see the different latencies. And again, you see that both things happen. There are latencies at which it gets worse and at which you improve the intelligibility. If you just compare that, then if we did the same as what the reviewers requested for the previous study, if we compare that average across subjects, and therefore since not everybody has the same best latency, if we look at the best latency in every subject and compare to the worst latency in every subject, you see that that is highly significant. But we again looked for a sinusoidal modulation, because you can think of maybe there is something in there, even though in average that does not need to be present, and therefore we did the following. We again ordered them according to where do they have their best latency, and then we fitted sine waves, and here you see that done on average, and here you see that for all the single subjects. And yes, that works nicely. Everybody has a best latency where there is a significant modulation of the intelligibility, and also other latencies where it gets worse. All right, and now I do have some time to introduce to you some thoughts about our concepts, because we were all talking about synchronization and resonance and the like. And I have a dear colleague, Jürgen Kurz, who wrote this book. And I went to his place in Potsdam and I asked him, well, you're the master of synchronization. Please let me know, how can I demonstrate that what we're seeing in the EEG is actually entrainment and not one of the other many phenomena? And the short answer is, show an Arnold tongue. The long answer is, read my book. So this book is really very interesting for everybody who speaks about entrainment, I think. And I'll give a brief summary of what I learned and what I think is important. And I'll start with a system that does not oscillate at rest, but it can still show some phenomena. I have such a system here. This does not oscillate, you will all agree, right? But it will do two things. Can we switch the mic to the... it will give you an impulse response. Right? But you can also make it resonate. Not oscillate, but resonate. And when you just observe what the system is doing, you just see an oscillation. And you don't know, are you looking... If you're only looking during the stimulation, it's very hard to tell apart a system that is resonating and a system that is oscillating. If you drive it at the right frequency, you get a very strong response. So the resonator does not oscillate at rest. It cannot show entrainment per definition. It has a resonance frequency, so it can show resonance, and it can show impulse response. And if you look at the frequency at which it oscillates, it will always oscillate at the driving frequency, at least after some... I don't know how that intermediate region is called. And then what we're all after are oscillators. We do have brain oscillations, at least some people still believe that after Jonas' talk, I hope. And the physical model would, for example, be a pendulum clock. These are the pendulum clocks of Christian Huygens, who first demonstrated that there is oscillation, that there is entrainment. So we're looking for these Arnold tongues. And the differences are the oscillator does oscillate at rest. It has an eigenfrequency, and the interesting phenomenon is what I showed in the Arnold tongue. It can switch between these two regimes. It can either oscillate at its eigenfrequency if you leave it alone, or if you're too far away with your driving frequency from the eigenfrequency, or it can oscillate at the driving frequency if your driving frequency is close enough to the eigenfrequency. So this system can show entrainment and can show phase reset. And I don't know, this is not going to be complete, and you may not like all of these, but I think that the following stimulation methods can lead or should be explained by the following mechanisms. Let's go through that one by one. If I use repetitive sensory stimulation, this can be auditory steady state, this can be visual flicker, whatever. If you do it at the eigenfrequency of n oscillation, say the alpha oscillation, then you can in principle get entrainment. If you use repetitive sensory stimulation at another frequency than the eigenfrequency, you will again get a steady state potential, but it cannot be explained by entrainment. That is most probably a superposition of impulse responses, as Joachim Groß showed nicely in a recent paper. I don't see him anymore. Then, if you use repetitive TMS at the eigenfrequency, this is just a huge impulse as compared to the size of the oscillation. This would not be considered entrainment by the authors of that book. As already Jonas said, only weak interference is considered. So that is probably a phase reset. But again, what you observe is a steady state potential. So that doesn't tell you anything. Then if you use RTMS at another frequency as the eigenfrequency, probably, again, you get impulse responses. Cannot be phase resets because there was no oscillations beforehand. And again, you would observe the same. Now, I wanted to classify tACS as compared to all of these others, because we know tACS is not able to be super threshold and to make a silent neuron fire. But if you apply tACS at the eigenfrequency or close to the eigenfrequency of a brain oscillation, then we believe you can achieve entrainment. However, we and others have tried to apply tACS also at other frequencies than the frequency of an oscillator, and then you don't see anything. And well, that will tell you something, but that's also to be expected. And I'm looking forward to what you think of this attempt to get a classification scheme of what we're all doing. And my take-home message to you is that tACS can modulate parameters of brain oscillations. I showed you mainly the amplitude, but we're also trying to modulate the frequency and, of course, the phase of oscillations or the phase relation of multiple oscillators. And in turn, this modulation of an oscillator leads to modulations of cognitive processes and demonstrates the causal role. And most interestingly for you probably is that if we use speech envelopes to entrain the brain, that modulates speech intelligibility. And I'll be happy if more of you try this approach. I'll be happy to help. During the conference, I learned that already 4 other groups are trying to use very similar approaches, and I'm very happy about that. And with that, I would like to thank you for your attention and my group for doing the nice work.
So thanks, Christoph, for the nice talk. I'm going to make the same remark that I did to you in private yesterday, just for everyone else. So we are trying tACS with a low gamma oscillation at 30 hertz, with the idea that we could boost some sort of phonological chunking. And we measure auditory steady-state responses before the simulation and after the simulation, and also behavior. So we had a very strong hypothesis about what it should boost and that it should have an impact on phonological performance. We do have an improvement in performance, but we don't see anything in the ASSR responses. So there might be explanations, but I mean, I think we have to be really careful what we really do with the tACS, because obviously we do something, but we don't know what.
Yeah, thanks for the question, because I have a nice answer to that. We tried the same thing. We seem to think along the same lines. We also recorded the ASSRs across many different frequencies and looked for the ASSR peak, which is typically around 40 hertz. And then we stimulated the subjects with tACS slightly below their ASSR peak and slightly above the ASSR peak, but not like 10 hertz away, but only, I don't remember exactly, 2 or 4 hertz away. And the interesting thing is that speeding up the ASSR was possible, but slowing down the ASSR peak was not possible. And we saw also a change in behavior, because we were able to show that the frequency of the ASSR correlated with the gap threshold detection. So if you have a fast ASSR, you seem to be able to localize short gaps in sounds. And that was even improved if we speeded up the ASSR.
But the behavioral effect.
That was the behavioral effect.
But our behavioral effect, where does it come from?
But don't you think you can have a behavioral effect and not see an ASSR? The ASSR, in our case, the behavior was recorded while we stimulated with tACS, and we looked at the ASSR afterwards. And we don't know how long that remains, and therefore we only checked a couple of points of the ASSR and not all of the frequencies.
Yeah, fair enough.
That may be the explanation, but...
Benedict?
Yeah. Is it on? Yeah. Okay, so Christoph, in the first half of your talk, you showed that you can use tACS to modulate hearing threshold, which is very nice. But how can you rule out that you're not doing exactly the same thing in the speech study? So you modulate hearing thresholds, and that has consequences for all kinds of auditory processing, but is not specific for speech.
Okay. This wouldn't actually bother me. So you would say the reason why they understand the speech better is not related to a higher order language area, but it's related to better perception of the sounds in primary auditory cortices.
Yeah.
That may be an explanation of why we see the effect. For me, that would be completely fine.
Okay.
Ole? You were. Oh, sorry, Jonas. It's, you should bring a beard.
I bring a beard next time, no problem. So Christoph, this is was really great, and thanks for this sort of taxonomy in the end that you gave us. I mean, with the impulse response versus the entrainment. What I'm trying to bring together is basically what you showed us and what Christoph Kaiser just showed earlier. So basically, I'm asking what is happening. What is missing here is when you stick in this complex envelope of a speech waveform in your tACS, when you we call this still, how do you call this? Envelope-tACS, basically.
Yeah.
When you do this, like what is happening? Like what's happening physiologically probably hinges now on whether if I have a delta band oscillator, let's assume for now there is one at 3 hertz in A1 or something. Let's assume, or 1 point something hertz. I don't know, but there is a delta oscillator. So, and this gets now hit with this envelope. Is this a phenomenon where this goes, is this a resonance phenomenon and that this oscillation gets modulated by it? Or maybe it's also interesting to hear what somebody like Christoph would say, because Christoph was a bit more careful whether there's an oscillation or whether it's just slowly drifting, fluctuating activity. But so are you assuming that your tACS envelope is somehow then affecting also baseline excitability of this piece of cortex depending on the ongoing oscillation? Or I'm sorry, now it gets...
But I already got your question. So we're not using a sine wave, and therefore, strictly speaking, at least in the book about entrainment, this case is not considered. And therefore, maybe one would not call this entrainment. But actually, one of the former students of Jürgen Kurz, Jan Freund, who is also now in Oldenburg, wrote his habilitation about I don't know whether he called it quasi-periodic or stochastic resonance or entrainment or synchronization. I think he called it synchronization. But they were able to show that if you have an oscillator that has an eigenfrequency, say around 10 hertz, your stimulation doesn't have to be exactly a 10 hertz repetition rate, but it can vary. So if the average frequency or the average interstimulus interval is 10 hertz or 100 milliseconds, you can still entrain this oscillator. So maybe what we're seeing is entrainment, but I'm happy to hear what Christoph is saying.
Actually, I'm a bit worried with the long latencies that you used. I don't know why you used 50 milliseconds and much longer, because in neural terms, that's enough to go from auditory cortex to prefrontal cortex and back and forth and back and forth.
Okay.
And at least if you believe this happens in early auditory areas, you should probably more use 10 millisecond intervals. And I think one of the biggest differences you had was actually between 0 and 50 milliseconds in the speech entrainment. So if you believe you're tapping into this auditory cortical entrainment, I think you have to look at much smaller delays between the text and the speech.
We can try that. We were thinking the biggest response we see in the scalp EEG to an auditory stimulus is, for example, the N100. And therefore, we figured we use latencies around 100 milliseconds. But we'll just try that. That's a good idea.
Pascal?
Yeah, I have a question about this dissociation that you made between entrainment and resonance, or oscillator and resonator. So, of course, I understand the resonator is not spontaneously oscillating, opposed to an oscillator. But is it really, I mean, you said it cannot entrain, and it will not show an Arnold tongue. And maybe I should have read the book by Pikowski, Rosenblum, and Kurtz more carefully, or memorized it better. So I don't know what exactly they say about it. But, I mean, intuitively, I would think that a resonator should be also drivable by something that's not right at the resonance frequency, right?
Absolutely.
Like, for example, when you did your
is
little
true.
experiment with the glass, I mean, you basically put in some kind of broadband excitation there, right?
Right.
It's like sticking and shifting of your finger, and still it resonates at a particular frequency that is specific.
No,
to
it always oscillates at the driving frequency. There is an intermediate region where you see the resonance frequency and the driving frequency, but in the eingeschwungener Zustand, in the steady state, in the steady state of the system, when you drive it, it only shows the driving frequency. But if you only look at the amplitude, if the driving frequency is close to the resonance frequency, then the amplitude is of course much higher than at other driving frequencies.
I guess we agree on this. So I guess if your driving is a bit broad, it will resonate strongest at its own frequency, right? I think there's no conflict there. But will it not also show something like an Arnold tongue then? Like if you drive it very hard, it will close to its resonance frequency, it will follow. If you drive it weaker, you have to be close to its resonance frequency to get the resonance. Right?
Okay, I get your point, and that's really very tricky, and that's why I said that's only the short answer. The long answer is read my book, because there are many further things shown in the book. What you have to show in the Arnold tongue is not the amplitude of the system, but you have to show a parameter that represents the phase locking between the signal and the driver. And he said the Arnold tongue is already pretty cool. Nobody has shown that for EEG, he said. But even what would be unequivocal proof, he said, I'm just using his words now, is that if at the border of the Arnold tongue you find phase slips, then that is proof that you are entraining a system that has an eigenfrequency, because this can never happen in a resonator system. The resonator will never jump back to its own frequency because it doesn't have an own frequency. And that is exactly what you see in the EEG. If you're at the border of the Arnold tongue, you see that it jumps back and forth between oscillating at, say, 10 hertz and oscillating at your driving frequency of 11 hertz, and then there are phase jumps if you look at the delta phase between the stimulator and the oscillator. Okay. Yeah.
So I would like to know which is the way that you think that is better to be sure that we are rather in an entrainment or in an impulsion. So I think that is
yeah. It's a very good question. I think it's one of the first sentences in the book about synchronization. They say, from only observing the physiological observation, there is absolutely, or it's very hard to differentiate between the different cases. You have to make assumptions about the system, so you know whether your system oscillates or not, and you can stimulate it at this frequency or not. And then there. This can always happen, of course, yeah, but then there is entrainment, but you don't see it. But these phase slips are what you should be after. If you find that, then you're sure you're entraining a system.
Sideways to your very nice talk, thank you. And that's getting at mechanisms underlying all of these stimulation techniques. Do we know anything about which class of cells might be more affected by the stimulation? For example, you have multiple classes of inhibitory cells and classes of excitatory cells. And if different ones of them are affected, that gives you a better sense about what the stimulation is actually doing at the level of neuronal circuits. I understand that that's probably not where the field is now, but I'm asking you to comment on what the field knows about issues like that.
This is a very nice question, but actually this is the type of question that we as experimenters ask you as simulators. And Flavia Foley has one person in the group who is doing network simulations, and together with him we're currently doing a network simulation where we simulate the stimulation of the network, and where we can look at how the excitatory neurons and the fast spiking neurons respond to the stimulation. And we do that for many frequencies and many intensities and look for Arnold tongues. And it's not final yet, but it looks like that the excitatory cells have their Arnold tongues at a different frequency than the inhibitory cells. And if you just compute the LFP across all of the cells, then you get a mixture of these overlapping Arnold tongues, and it's a very confusing picture. But if you, instead of computing an LFP, just show the Arnold tongues of the membrane voltages of the single cells, then you can nicely separate how the excitatory cells and how the inhibitory cells react to the stimulation. And the main difference is it happens at different frequencies.
I see.
Well, if I may inject, I thought Nancy, when she raised her hand, would like to say that there are, that resonators is a system which is steady state response, representation, and there are dynamic system representations of oscillators that might be better, in terms of looking at this phenomenon of resonance, because they may behave differently closer or out of the tuned frequency.
Right, that's why all of the physicists that do that always look at systems for which they have a differential equation that they can use, and then they know what they're doing. But we don't have a differential equation for the brain. We can only stimulate it and observe some EEG parameters. So we have to go this byway.
Just let me answer. What you're doing sounds perfectly reasonable to me and very interesting.
Thank you.
Okay, I will now. This is another example of the useful interaction, which we should have more of, between physicists, modelers, physiologists, to clarify the concepts we use. So thank you, Christoph, for raising all this.